Naturally, we are very honored to have Professor Singh from UC Irvine. So, Professor Singh is a professor of computer science at the UC Irvine. He's working primarily on robustness and interpretability of machine learning algorithms, along with models that reason with text and structures for natural language processing. So he has won many awards across national agencies and companies. He also has won many paper awards. So without further ado, I'll let him start his presentation.
Thanks, Lily, and thank you for inviting. And yeah, thank you for being here. This talk, I haven't explicitly worked on interpretability because last couple of years I've been trying to figure out what it means in this new sort of era. And it's great to have this workshop solely focused on those kind of ideas. But there are some related things that I've been exploring and just want to see what people's take are on those kind of ideas. And I feel like a lot of methods can be classified as sort of explaining in the dark, and I'll sort of say what I mean by that, and then would be great to hear what you guys think. Okay, so when we started working on explanations, to me, the most important use case of explanations were almost as a proxy of evaluating generalization, right? So like, given a model, does it actually generalize beyond the prediction that we're looking at? Explanations give you a way to understand that. So going back almost a decade, I guess, at this point, we had this paper where we were looking at image classification, and you would look at some original image that was classified as wolf, for example. And then you would be like, hey, why is it actually doing that? And you could look at an explanation, which is basically saliency map, or a bunch of techniques have can sort of be distilled into the same particular idea, which is to figure out which features were most important for the model. And if the explanation looks like this for a model, you would say, okay, the model is kind of looking at the fur of the animal, and maybe this is a good model. And an explanation that doesn't do that, but instead is focusing more on the ground, the fact that there's snow, to figure out that this is a wolf, might still be accurate, but it wouldn't be a really generalizable model. You wouldn't want model B here, you would want model A. And so in general, we had this whole intuition as a community that if explanations look right, we trust the model to generalize to some degree. And this was sort of the basis of interpretability for a while. Now the things have changed quite substantially, where I don't think this idea quite applies as it stands. And they've become complex in some sort of substantial ways. One of them is that we've gone from simple functions that capture behavior of these models to these models becoming so complex that simple approximations over their behavior don't really hold in. We used to be in this world where features used to capture patterns in the data. If you're focusing on a feature, that meant you've learned a specific pattern. But now the size of the training data has become huge. We have much more complex pipelines of like post-training and things like that. And so memorizations of patterns or memorization of data is a lot more nuanced. I wasn't hearing voices stuff. Always good to get a reminder. And then earlier, the decision subspaces, when you think of classification and regression, were quite simple, and you could explore all possible classes. Like that wasn't a big deal. But the complexity of the tasks that we are looking at now, which are generation and reasoning and a bunch of those things, it's not quite easy to explore the space of the output anymore. And so what this means is that if you're just looking at interpretable functions over the features or weights of the model, I feel like we are missing a larger picture. So what I'm going to do is I'm going to talk about some of the capabilities of these models and why explanations might be a little bit hard, and talk about certain behaviors, and we might want to seek an explanation for why they might be happening. Okay? And so this is work that we've been doing past couple of years. So these are not like GPT-4 style capabilities, but these are still models that are representative in some sense of what these models can do. So we can start with some basic ones. You know, if you ask them questions that involve some math, they can answer them. If you ask them to generate photo of an engineer, they can generate photos of engineers. If you ask them to generate slightly more complicated things where there are some compositions, tulip and a cup, it can do that. And there are obviously many, many other capabilities, but we'll sort of focus on these three and look a little bit deeper as to what might be happening. Now, there are some strange behaviors, even with these capabilities that I showed you, that come up if you look a little bit further. So, for example, it could answer this, but when we looked at what is 23 times 18, it gives an answer, and turns out it's a larger number, so you can pretty much say one of them has to be wrong, and turns out the second one is wrong. If you ask it to generate photo of an engineer, we saw one example, but if you actually look at the distribution, it's actually predominantly male, to a degree that there is only 10% female images generated. And this feels wrong, not just from a societal point of view, but even if you look at the training data set, the proportion of female engineers in the training data set is much higher than 10%. Right? So the model is behaving in ways that feel unauthentic in some sense to the training data. And then tulip and a cup, we saw a good example, but I kind of cherry picked it because for this model we were looking at, every other example you can argue barely has a tulip and a cup in it together, depending on how you define a cup, I guess. Maybe you could be generous about this one, but all of the other ones are probably not actually tulips. Okay, so the question then becomes, well, generalization is pretty tough to explain when these are complex behaviors, math, these models are complex, things like that. And if you only look at the input, output, and the model weights, it's very difficult to think about generalization as to what it means and what we're even talking about. Partly because we haven't got a good definition of what it means to be in distribution, what it means to be out of distribution, and it's kind of difficult to talk about all this. And so essentially the question is, how can we explain generalization or lack of generalization or get to any of that stuff without actually looking at the training distribution of the model? And so when I think about generalization, I guess what I'm talking about is a simple cartoon view of it, where let's just say task performance, whatever the task is, whatever your behavior is the y-axis here, and some notion of similarity to the training data distribution is on the x-axis. And I'm going to keep these things vague, and we'll make it concrete with a few examples, but deliberately vague here. And if you have a model that looks like this, where the task performance increases the closer it is to the training data distribution, versus a model that looks like this, these are very different sort of qualitative behavior. To me, generalization is one where the green one here is generalizing well, because it's not so sensitive to whether your input is close to a training data. And the other one generalizes poorly. And so if you have to use explanations and interpretability to try and differentiate between these two, you need to know what the x-axis is. Without x-axis, it's kind of difficult to figure out what the difference is between these. So what is the right x-axis? How can we even start thinking about it? That's kind of the topic of this talk. So what we will do in this talk is we will look at these three phenomena a little bit closer. The simple mathematical operations ones, simple compositions, and this bias that we saw in some of the generations, and see if there is a way to explain some of this by looking at the training data distribution, explain this behavior. And maybe that gives us some intuition that we should think about interpretability a little bit more closer to be data grounded rather than just based on the model. And then I'll end with some takeaways that are hopefully of interest to folks. Okay, so let's start with the math one, which we did it's been a couple of years now. So what we did was we were looking at a model that had pretty good performance, but it was not 100% correct. And this is circa 2022, so you can imagine what the models looked like then. And this is a language model, large language model. And so this example we had where it was getting this one correct and this one wrong. And to me, these are very similar. Maybe you can say mathematically one is slightly harder, but not quite. And the question is, do we have an explanation for why the model behaves differently on different instances? And how does it actually depend on the pre-training data? Like, is there something about the pre-training data that would help us explain why this is happening? And so what we did was, just as an intuition, we started testing something very simple. We just counted how many times does 24 appear in the training data of the model that we were actually evaluating. And it was approximately 10 to the power 7. And if we counted how many times does 23 appear just in the training data, it ended up being around 10 to the power 6. Okay. There's a difference here. Whether it means anything, we don't know. So it made us curious enough to try to explore this a bit deeper. So what we did was we created a bunch of equations where we tried essentially all first operand between 0 and 99. And then we computed the average accuracy for each of these numbers over any other second operand. And we plotted that accuracy. So, we would have like, what is 24 times x, and replace x with a bunch of numbers and average that accuracy. Is that 100%, 80%? How many times does this model get it right? That's going to be our x-axis. And our y-axis, x-axis is the frequency. How many times does 24 appear? And y-axis is what is the average accuracy. And so just for these two numbers, we saw 24 was about 0.6, 60% accurate, and 23 was a little bit lower. Substantially lower, I guess. But then frequency also was different, like 23 was less. So when we did this for all of the numbers, we saw a pretty surprising, or maybe not surprising, but we saw a pretty clear trend, at least, where there are about 100 points here. And the more often the number appears in the training data, the higher its accuracy tends to be. And the lower it appears in the training data, the lower its mathematical accuracy is. This is not quite an explanation, but it tells me that whatever the explanation is for why a model works on 24 and why the model doesn't work on 23 has to take into account something about how often it appears in the training data. And frequency here is the key thing. It's on a log scale. So just so that you see that. And these are still pretty high frequencies. We're not two-digit numbers. They appear pretty many times in the data set. And we continued sort of looking at much more detailed stuff. We looked at addition and multiplication, and we sort of varied the number of examples you're putting into the context, and we saw clear trends for different operations. We also tried really hard task of not even telling it what operation we are asking it about, but giving a few examples of it, like 2 or 4 examples. And even then we saw this trend where the numbers that it had seen more often, it seems to be much more accurate at than the numbers it hasn't seen. And these are, again, 2 digits, so it has seen them plenty of times. Okay. And so the conclusion of this kind of stuff is that the pre-training data, just simple counts, seem to have pretty high impact. And if you want to explain LLM capabilities without looking into these counts, it feels a little bit unsatisfactory. But of course, this method is very simple. We're using very simple counts. We're not doing very complicated things, and it's only numerical reasoning. So, it wasn't quite clear how much we can generalize this intuition. But the idea here is, if you look at this plot again, we are basically computing mathematical accuracy as the y-axis and putting unigram and bigram counts on the x-axis. And we are realizing that, hey, the model, at least the one we were looking at, seems to be a little bit more like this. And therefore, we sort of have some intuition that it doesn't generalize that one. Okay. So let's move on to slightly more interesting examples. This one is simple compositions where we have images where we want to generate objects. When we look at this particular model, this is a stable diffusion model where if we ask it to generate a single object, it's actually pretty good generating it overall. And especially if they're common objects, and accuracy of generating it is pretty high. But when you start looking at multiple objects, it kind of starts getting a little bit wonky. So when you do grapes and a watermelon, you'll see that some of these pictures, like this one doesn't have grapes, this one doesn't have watermelon. This one arguably also doesn't have grapes, but it's a little bit wonky. We saw the example of tulip and cup, and bicycle and skateboard was another example where there are very few instances where you actually have both. It's a weird mixture of one or the other. And so it struggles to generate images even for two objects, and it gets worse with 3 and 4. And you can say that, hey, the modern models are better at 3, but then are they still accurate when you increase it? Maybe not. So just to show you an example of 3 objects, a tulip and a cup and an apple. There are some examples, but you can see it's trying. But for the most part, it's not actually, none of them are actually generating 3 objects as we asked. Okay, so the question is, well, can we go back to the frequency again and see if we can explain this, right? So what we're doing is we're looking at generation accuracy, like does it contain the objects that we asked it to generate, and the frequency of objects in the training data. When you look at 2 objects, and we tried different models here, what we are showing here is the correlation of the generation accuracy to frequency of how often it appears. And you see that there's some positive correlation. It's not like 100% or anything like that, but it is significantly positive. And across the models, we saw this positive correlation, right? So I'm just computing the correlation of the chart, the plot I showed you earlier, where we are putting the frequency of how often do these pairs appear in the training data and the generation. See? And with 3 objects also, we were computing how often do 3 objects appear together in captions. And you see, again, low but positive correlations. Right? Correlations are, again, not explanations, but they at least nudge you that, hey, you should be looking at this. And we started looking at, okay, these are not good correlations, but we should at least try to understand what's going on here. So we started looking at the generations themselves and looking at the training data, right? So now we're not looking at generated images, we are looking at what's in the training data. And when we saw watermelon and grapes, here's what are all of the training data or some sample of the training data that contain both watermelon and grapes in the caption. And when you look at it, you can see, okay, most of these actually have watermelon and grapes in the images. In fact, we computed it, and about 80% of the images actually have a watermelon and a grape. About 20% don't, like this one doesn't, and so on. But if we look at a different pair of objects, like skateboard and bicycle, these are training data images that mention skateboard and bicycle, but none of the images actually have both. Maybe this one has both, but everything else doesn't have both, right? Even though the caption mentions it. And so in some sense, the quality of this data is pretty poor because all of these captions mention bicycle and skateboard, but only about 10% of them actually have both of those objects. Usually they have one or the other. And so maybe the caption counts, just counting whether bicycle and skateboard appear together is not the right one. We should be looking at the training data images and seeing how many of them actually have those objects. And so we compute this training appearance ratio, which is just a metric that says how many times do training data examples that mention 2 objects actually have those objects in the images, divided by the number of images that even mention those things, right? So just to be clear, for bicycle and skateboard, this number will be low because it's mentioned a lot, but the generations don't have them. Whereas for skateboard and grapes, watermelon and grapes, you get about 80%. And we were trying to see, okay, if we're not looking at quantity, but we were looking at this quality, does that explain what's going on? And so we went back to this correlation, and turns out that the appearance of this, like, does the objects actually appear in the training data, correlates quite well, right? That's almost 0.5 correlation on how well it predicts whether your accuracy will be high or not. And similarly, for 3 objects, we get a much higher correlation than just looking at frequency. Of course, these correlations are still, you should never look at correlation without looking at the underlying data. So I will show you that this is the underlying data where here's the training appearance ratio that we're computing. It's between 0 and 1. And here's the accuracy in some sense. And you can see that there's clearly a trend here, but the data is pretty nice, right? So similarly for 3 objects, clearly a trend, but the data is nice. And so this sort of tells you that, hey, the data, the number of times things are happening in the data has some effect on the accuracy of it. Okay. And so high correlation here implies that very little generalization is taking place. And the quality of the data here seems to explain the behavior of the model rather than just the quantity, right? Like how often do captions and images correlate seem to be really important. And they suggest that some sort of nuanced notion of matching is needed. You can't just do counts of things. You need to be a little bit careful about what you're measuring. Okay. And so if we go back to this plot, what we are saying here is the generation quality was the x-axis, the y-axis, and the x-axis was initially unigram counts, but then appearance ratio in the data is the one that we really looked at. And it seems to suggest the model is following this kind of trend. Just kind of explaining the behavior of the perception. Okay. For the last example, we look at the bias amplification one. It's a little bit different from just looking at the accuracy of generation. So yeah, just to remind you, we asked for a photo of a face of an engineer, and it generated a bunch of images. And the problematic behavior here is that it only generated one image out of 10 that was clearly a woman. And you can conclude that this sort of maybe it says that the model is biased, but is it just because of the training data or is something else going on? Something to think about. So what we did was we went to the Lion data set, which has about 2 billion image caption pairs. And there's this really cool tool that came out of AI2 called What's in My Big Data that sort of indexes all these images and text corpuses and easily makes it searchable for whatever you want. So this allows you to answer what does the training data say about this behavior. So what we did was we took the caption, photo of face of an engineer generated, and this was about 10% female. And then we searched for all captions that contain engineer in the data set and ran through some classifier that told us sort of whether it's a woman image or not. And we got some statistics from the training data. And turns out, yeah, it's not 50-50 in the training data, but it's 25%, right? 25% of generations are female. The model seems to be worse, much worse than what the data could suggest. The question is, why might this be happening? Is this isolated to engineers? And if you've been sort of looking at this stuff, you realize that it actually is not specific to just engineers, right? So what we are showing here is the proportion of the training data that is female for a specific occupation. I forget where engineer is, but engineer was like 25%, so somewhere here. But what is the generation percentage? And if these were matching very well, if the training data was perfectly explaining your bias, all the points would lie on the diagonal. So anything that's off diagonal means that you're not matching the training data distribution. And the red area is where you're more biased, and the blue area is where you're less biased. So all of these things in red are what is known as bias amplification, where you are more biased than what you're seeing in the training data. And the diagonal is bias preservation. And you can actually compute how much your total bias is. And turns out that stable diffusion amplifies bias considerably for occupations, about 12.6% compared to the training. And this is the data that was actually. Okay, and turns out this is not a new behavior that we've seen. It's a well-studied problem. People have talked about bias and bias amplification like quite often, and there have been sort of media stuff. Kaiwei is giving a talk, but he had a paper a couple of years ago that was also looking at this. that talked about bias amplification. So when we started looking at this, we were like, hey, we need an explanation for why bias amplification might take place. And then the question was, are we looking at the right data distribution when we're talking about generalization and bias amplification, right? Are there more specific patterns that would explain behavior rather than just looking at the whole corpus and seeing what's going on? So, as a way to do this, we realized that the captions and prompts that we ask the models are actually very, very different from each other, right? So our prompt was photo of a face of an engineer, but an actual caption looks something like this. Portrait of a smiling young female mechanic inspecting a CV joint or a car auto repair shop. Here's another one. Muscular bearded athlete breaks quarter after good workout session. Portrait of a salesperson standing in front of blah, blah, blah. These captions are nothing like show a face of an engineer, show a face of a salesperson or an athlete. It's clearly much more descriptive in a way that we can also argue that, sometimes it's explicitly mentioning what the gender is. Sometimes it's indicating what the gender is. So this mismatch between the captions, the actual data, and what you're prompting can maybe impact the bias measurements themselves. And consequently, we think bias amplification is taking place because we're looking at the wrong condition. So one thing we did was we ignored all captions that explicitly mentioned gendered language, right? Like, so we ignored from our counts anything that mentioned male, female, man, women, like that. And recomputed everything. So what this would mean is instead of 10% versus 25% over the whole data set, we would get rid of all the images that mention the gender, which ended up being quite a few of them. But it turns out that the rest of the images, especially in this case, became much closer to our generation quality. So if you don't have gender in the caption, which is the case here, your data set actually starts matching your bias that you see. In fact, we did this over all the occupations, and you can compute that it doesn't go to 0, but just removing gendered language seems to reduce the bias amplification considerably, suggesting that the model is not amplifying bias. We didn't have the right explanation for what's going on. The other thing we did was we started looking at sort of semantic mismatch. So we would generate things like photo of a president, and it would generate stuff like that. And then we would say, look at all the images that contain president. And apart from the captions, the images themselves look really, really different. Like none of these images, if you just squint, look nothing like these, right? But then we started looking at the captions, and we realized that the captions are actually very, very different. These are sort of what the captions look like. These are still presidents. They're just not photo of a president the way we mean it. And so we started looking for captions that are semantically close to photo of a president, like using a nearest neighbor semantic distance search. And then when we look at the training data images, they look like this. And if you squint, they look a lot more like this than just all images that mention president, right? So the idea here is that maybe we shouldn't be looking at just captions that mention president. We should be looking at captions that are close to the prompt that you're testing in order to explain what's happening. And in this case, the bias amplification reduces quite a bit from 12% to 6.8. And it's kind of difficult to see visually, but you'll see a lot less stuff in the pink, a lot more on the blue, and even the stuff on the pink is closer to the diagonal there. Yeah. And then these are since distributions, we can sort of take the intersection and we can say, okay, what if you only consider the training data where your captions match and they're both semantically and in terms of gendered language, and turns out that reduces the bias amplification to 4.3, which you can argue is not much bias amplification. Some of it is happening, but if you look at this, there are about as many in blue as pink and so on. So we tried another experiment where we were like, okay, let's just make sure that what happens if we match the training data exactly, right? So we only prompt the models with captions that we've seen in the training data verbatim, instead of using photo of a face of an engineer or something like that. And so we get rid of any mismatch that's between captions and prompts. We're literally taking captions from the training data and generating the image and seeing what does the bias look like. That's using identical text, and then we measure bias. Does it reduce bias amplification or not? And it turns out that when you do that, you get all of the points pretty much on the diagram. So there is no bias amplification when you're actually using captions from the training data. It's 0.06% with whatever. And negligible, right? And so this is a way to sort of understand that is there bias amplification or not? When you look at the data, when you actually start narrowing down into specific subsets of the training data, you get clear explanations for this behavior. And that sort of explains why we see bias amplification, even though all we're doing is log likelihood training. So it shouldn't have any bias amplification. Right? And so going back to this sort of figure, we are talking about the task performance here as how much does it match our expected bias. And when we look at different ways of matching the training data distribution, we see that the model, the more closer you are to the training data, the more it matches, right? So the training prompt would be all the way to the right, and nearest neighbors and gendered words and counts, they all go sort of further and further away from what data distribution the model is actually focusing. And so we can conclude that this model also is not really generalizing that much. Yeah. Okay. And in this case, I guess it's a good thing because we don't want it to do bias amplification. We want it to be at least not worse than what's in the training. Okay. So what have we actually included, right? So in summary, what I've shown is we looked at these three somewhat complex behaviors, doing math, composing objects, and this notion of gender bias in generated images. And turns out that in each of them, training data was the key to understand the behavior. It gave us a bit of an insight into what was going on. But we were sort of looking around for patterns, and we found the right patterns that can help give us some notion of generalization. And in this case, the model seemed to be generalizing less than we would think otherwise. And so when I think about interpretability and explanations, it feels to me that we have to have methods that are grounded in the data that the model is looking at. The weights and everything are encoding a lot of essentially distilling the training data. So if you're looking at interpretability and ignoring the training data, you might be getting something that's not quite accurate to how these models learn and behave. This is not it's not an easy thing to do, just to be clear. We have to make lots of simplifying assumptions and stuff, and many of them are probably obvious to people here. But I'll tell you why we had to do this. One of the biggest problem is opacity of these models. Training data sets are not available easily, and that is just the smallest part of it. The bigger part of it is that the pipelines that are involved in training models are multi-stage and complex. And so even if you have access to some pieces, you don't have access to most of them. So what we did was we relied on proxy data sets that are publicly available. Sometimes they match the actual data set well, sometimes they don't. And we sort of ignored the whole post-training thing here, and that's not the right thing to do also. But we had to make these assumptions because of this problem. Scale is another huge problem here. Training data sets are massive, and any sort of non-trivial measurement is computationally very hard, which should get computer scientists excited because that means there are computationally hard problems to solve here. But what we did was we relied on simple counts and clever indexing and things like that to get what we could. And at the end of the day, we are measuring correlations. We are not measuring causations because, again, causation would add another whole dimension to the complexity where you're like, okay, what if we had to take this piece out of the training data? What effect it would have? And again, people who like hard problems have hard problems. So, and the final piece was even defining, right? Like it's unclear what the right training data set is to be looking at for a specific behavior. The behaviors can sort of be learned from different subsets of the training data. And we found some good, strong patterns based on intuition and things that are targeted to specific behaviors. But it's difficult for me to think about, at least right now, just given a generic behavior that you want to explain, how would you find the right data set that would explain it? I think that's also a pretty exciting research problem that people should be thinking about. Yeah, so with that, I will close my talk and take questions.
Thanks, Samir, for the excellent talk. Any questions from the audience?
Hey, thanks for a wonderful talk. I'm very much aligned with you thinking about data and when we think about these kind of problems, but I'm curious, a lot of what you talked about is kind of focused on post hoc analysis. So you have some data, you have a model that's trained, and then especially because the data is so big and because there are so many axes on which we can look for correlations, it ends up being almost reactive rather than kind of anticipatory. Do you have any thoughts on how we might move towards a direction of kind of discovering the biases as opposed to just measuring them once they are already imbued?
Yeah, no, that's a great question. We also tried some methods, especially I think there's a whole line of work on influence functions and data influence function and data shape functions and stuff like that. I think computationally they were just really, really hard to work with. Right? It just becomes this problem of like, what approximations can you make to get some number? But I think influence functions, even with the original models, the approximations they were making were often not accurate, and that just led to claims that just weren't accurate, right? So I think, yeah, if there is a way to draw that connection and do, like, given a behavior or like a test data set that captures the behavior, find the training data, why it happens, that would be a great method. But again, there was one thread of work where we were doing that, and part of validating that would be to take away subsets of the training data, retrain the model, and see if the behavior persists. And we saw some signs, but it was way too noisy. Exactly. Yeah. Even for small elements, that's really hard. So it's not even clear how much that would generalize to bug.
Thanks, it's very interesting. So I think one thing it seems like these results that it is suggesting is that models in substance are a reflection of their training data.
Yeah.
So do you think, is there anything different that happens at scale? Like, for example, some people would maybe say that like there's some emergent behaviors that happen at a certain point where maybe like models are doing something different. Like, do you think that is the case, or do you think that something like this still holds even when you're looking at a much larger models trained on much more data?
Yes, that's a great question. And I think that we sort of assume that maybe there's some generalization happening that's emergent, but it's difficult to prove that it's happening, right? And part of the goal for this was to test that hypothesis. And like we were always saying, like if we found really good correlations, that means there isn't, right? And maybe people will argue even with that characterization. But to me, it's very difficult to say, hey, I've searched through all the possible ways this model could have learned this, and I can claim that this is generalization, right? I think what most people do is verbatim, hey, this instance or this mathematical word problem hasn't appeared in the training data, therefore it's emergent. But yeah, that's been suspect, right? Like we just reaching the limits of how much we can do with data. Yeah. We had one piece of work, which is also what Judy's question was pointing at, like which was trying to explain chain of thought, and then there was a lot of stuff where emergent stuff comes because of this reasoning parts. But there also we saw evidence that there are pieces of that in the training data. So whether it's emergent or not, it's unclear.
So let's consider the third example that you were giving. I think like when you think about this prompts as defining distributions, then I've also heard like these kind of like models of defined biases.
Yeah.
But it's clear as you were showing that it is more of a kind of like issue of you comparing the wrong distribution. If you're comparing distribution, yeah, of course you're observing the variable of gender, but you're comparing it condition on being a person versus being a person who is an engineer. So of course the distribution is going to be different.
Right.
So I guess like that is kind of the clear explanation to this. But then, like, I guess moving forward, I can see how you could maybe try to correct this distribution after the fact. So maybe you say something like, whenever you have one observed like a generation such that it is a person with any profession, you kind of like artificially say gender is 50-50. You could do that, or you could, on the other hand, kind of like really put effort into curating the data sets that are going to be reflecting the distribution that maybe you want to see. Right. I can see maybe both approach. In some cases, I think like in some more programmatic context, maybe the first one would be better. But I guess in some like more human like domains of kind of like what we're seeing more that are require the human kind of knowledge, maybe the second one would be.
Yeah, so I mean, I would say I stay away from trying to fix these problems. It's much more fun to just keep pointing at these things. But between the two, I would say a lot of the post-training methods tend to be more on the latter side. Like, hey, the pre-training stuff, the model learns whatever it learns. But then let's start looking at realistic use cases. So like people will not say photo of a blah, blah, blah person. They'll just say photo of an engineer. In those cases, let's make sure that the generation quality is good, right? Like, I don't claim anybody's post-training for bias directly, but at least the real world prompts end up being a part of the post-training. And how much that fundamentally changes the behavior of these models and stuff is kind of fun, right? So even with the stable diffusion models we're looking at, some of them have post-training and where that happened, but we still saw pretty good correlations, right? So I think the difference between these models when we looked at them, let me show you. I guess that's way too far, was because of the post-training stuff. But some of these capabilities don't go away. That's a good question.
I got one question. So do you see that, for example, this kind of model, so today focus on data side, do you see like, so there are some techniques try to understand, for example, the model's behavior at the concept level. Do you see that those techniques can be combined with the approach to better understand the bias?
Potentially. I mean, I think what they could do is definitely help us find the connection between data and model weights, right? And so concepts can almost be the middle ground. I think the concept stuff still is an approximation of what might be happening internally in these models. And so, yeah, as an avenue to get to what data might be most important, I think they're pretty useful.
Any additional questions? Yes, okay, now the next thing, Samir again. Right.